If you recall, we had started looking at the computation of product measure of a set E in the product sigma algebra, and we had shown this can be computed via the sections of the set E, integrating the sections and taking the measures. So, let us recall this result, and then we will continue to generalize this result for functions which are non-negative and integrable functions. So, let us recall the result that we had proved last time, namely if x a mu and y b nu are two sigma finite measure spaces, and the product sigma algebra product space is x cross y, a times b and mu cross nu is the product measure space, then we showed that for any set E in the product sigma algebra, the measure mu cross nu of E can be computed by either taking the section of the set E at a point x, and that gives us a subset of the set y, and we showed that this is in the sigma algebra. You can take the measure of this section. So, this becomes the function of the variable x, and then you can integrate out this function with respect to mu to get the product measure. Or equivalently, you can take the y section of the set E, that gives you a subset of x, which is a measurable set, and then you can take the measure of mu measure of that gives a function of y, and then integrate out that with respect to y to get the measure of the set E. So, this result we want to reinterpret as follows. See, the measure of the set E x can be written as the integral of the indicator function of the set E with respect to the product measure. So, the mu cross nu of the set E is nothing but the integral of the indicator function of the set E on one hand. On the other hand, if you look at the x section or the y sections, they are nothing but the indicator functions of the set E again. So, when you take the integration with respect to y, that means you are fixing x. So, you are looking at the section of E at x. So, nu of E x is nothing but the integral over y of the indicator function of E with respect to the variable y, and similarly the other variable. So, as we had mentioned, the importance of the result, this result lies in the fact that the indicator function of a set E is a function of two variables, and to find its integral with respect to the product measure, what we can do is we can fix one of the variables, say x. This becomes a function of one variable y, and one shows that this is integrable with respect to nu. So, when you integrate out with respect to nu the variable y, this is a function of x, which again can be integrated with respect to mu, and this integration gives you the integral of the indicator function of E. So, the important thing is that here when you are integrating with respect to y, the variable x is fixed. So, this is only a function of the variable y. So, for every x fixed, you treat it as a function of the variable y, integrate that out, and then integrate out that integral with respect to the other variable. And similarly, we can interchange x and y and get the result. So, what we want to show is today is that this result is true for all non-negative measurable functions on the product space x cross y. So, the theorem we want to prove is the following, namely, if f is a function on the product space x cross y, and it is a non-negative function, which is, so f is a non-negative measurable function on x cross y is measurable with respect to the product sigma algebra, then the following statements hold, namely, if we fix one of the variables, say x. So, if x naught is fixed, then consider the function f of x comma y naught, and similarly y goes to f of x naught y. So, for the function f of x y, either you fix the variable y at y 0, or you fix the variable x at x 0 and treat it as a function of one variables only, then these functions are measurable on x and y respectively. So, what we are saying is that for a function of two variables, if it is measurable with respect to the product sigma algebra, then fixing either of the variables gives you a function of other one variable, which is measurable on the corresponding basis with respect to the corresponding sigma algebras. and these are non-negative functions. So, you can integrate them out. So, if you integrate this function x going to f of x y naught with respect to x, mu, then that gives you a function which depends on y. So, the function y going to integral over x of f x y d mu x. So, you integrate out the variable x, this gives you a function of y, and similarly you integrate out f x y with respect to the variable y, you get a function with respect to x. So, the claim is these two are well defined non-negative measurable functions on the respective spaces. And finally, these are non-negative measurable. So, you can integrate them out with respect to the corresponding variables. So, if you integrate out them, so first integrate with respect to y and then with respect to x, that is same as integrating first with respect to x and then with respect to y, and both are equal to the integral of the function f of x y with respect to the product sigma algebra. So, this gives an extension of the earlier result, and so it says that for non-negative measurable functions, if you want to integrate with respect to the product sigma algebra product measure, then you can do it one variable at a time. So, these integrals, these two integrals are called the iterated integrals. So, the claim is that for a non-negative measurable function, the integral with respect to the product measure is equal to the two iterated integrals. Once again, the importance being you are integrating one variable at a time. So, let us prove this result. So, this proof is going to be built up step by step, and this is what I call as the simple function technique. So, the idea is that when f is the indicator function of a set, this result is true by the earlier result on product measures, and then by looking at, because all the integral everything involves integrals. So, and integration being a linear operation, we will get that from that this result is true for non-negative simple measurable functions, and once it is true for non-negative simple measurable functions, a application of monotone convergence theorem will give us that the result is true for all non-negative measurable functions on the product space. So, that is the approach basically we are going to follow, and this is what I call as the simple function technique. When you want to prove something for non-negative measurable functions on a measure space, verify it for the indicator functions, verify it for the non-negative simple measurable functions, and then verify it for the limits of non-negative simple measurable functions. So, let us prove this. So, the step 1 is that the required claim holds when f is the indicator function of a product indicator function of a set E in the product sigma algebra. So, let us look at that. That was what we have already shown. When E is, so step 1, when E is an element in the product sigma algebra, we had already shown that the product measure mu cross nu of E on one hand is equal to, you take the indicator function of E and integrate out with respect to x d mu, and then integrate out that with respect to the variable y. So, d nu, and that is same as you first integrate out the indicator function x y with respect to d nu, that means keeping the variable x fixed, you are integrating with respect to y, and then compute the integral of that with respect to the variable x. So, these two are equal, and the middle thing, if you recall, we said it is equal to the indicator function, integral of the indicator function of E with respect to the product sigma algebra. So, this is precisely saying that the claim holds for f equal to the indicator function of a set E, E belonging to the product sigma algebra. So, this is step 1, and now from here we want to go to step 2. So, let us so step 2 is, let us take a function. So, step 2, the required claim holds for non-negative simple measurable functions. For S f equal to S, a non-negative simple measurable function on x cross y. So, let us take, so what does the function look like? So, a non-negative simple function S on the product space looks like sigma a I indicator function of some sets E I, where I is 1 to n, and these E I's are sets in the product sigma algebra A times B, and their union of E I is their pairwise disjoint, and their union is equal to x cross y. Right. And now, by step 1, what does step 1 say? Step 1 says for each E I the claim holds. So, step 1 says for every I equal to 1, 2 and so on n, the integral of the indicator function of E I with respect to d mu cross nu, on one hand it is equal to the integral over x, integral over y of indicator function E x y d nu and d mu, and also equal to the integral over y, integral over x of the indicator function of E d mu and then d nu. So, this is what we know. Now, let us just observe, because this is true for every I and integration is linear. So, that means, if I multiply, I can multiply throughout by a I. So, if I multiply by a I, so I can multiply here by a I. So, this is E I. So, if I multiply, so this is a I, and I can multiply by a I, and I can multiply here by a I, and then take the summation. So, sum over I, then so summation over I, and here will be summation over I, right. Now, this summation integration being linear, I can take the summation inside. Okay. So, when I take this summation inside the integral and then again take it inside, I will get summation of a I times indicator function of E I integrated with respect to nu, and then integral with respect to mu is equal to this. I take it inside, that will be summation of a I. So, let us just write that. This is more of writing than understanding. So, when I do this summation and take the summations inside, I will get integral over x, integral over y of summation I equal to 1 to n a I indicator function of E I d nu d mu is equal to. So, that is equal to, and this summation inside will give me integral over x cross y of summation a I indicator function of E I d mu cross nu, and the last one will give me integral over y, integral over x of summation I 1 to n a I indicator function of E I d mu d nu. So, this is just using the property that for every indicator function of a set, the result is true and integration is linear. So, the result is true for finite linear combinations of these things also. So, this gives us and this is precisely my function S. So, this says integral over x, integral over y of S x y d nu d mu is equal to the integral over the product space. So, this is the function S. So, S of x y d mu cross nu, and that is also equal to the other iterated integral, integral over y, integral over x of S x y d mu of x d nu over we have already done it. This is over y. So, over y that should be nu actually, and this should be mu, sorry, because this was over x. So, that should be, no, that was okay, that was d mu and this is d nu. So, this is over x. So, d mu and d nu. So, that is okay. So, this says that the result holds. So, this proves the second step, namely the claim holds for f a non-negative simple measurable function. So, now from here to go to general non-negative functions. step 3 says we should be able to prove the result when f is. So, let us take f on x cross y to r star f non-negative f a times measurable with respect to the product sigma algebra. So, now we look at the characterization of non-negative measurable functions. F being non-negative measurable implies that there exists a sequence S n of non-negative simple measurable functions S n of x increasing to f of S n of x y increasing to f of x y for every x y belonging to the product set x cross y. So, that is because of the fact that this is by the. So, this is by the fact that for every non-negative measurable function there is a sequence of non-negative simple measurable functions converging to it. Now, by step 2, so by step 2 we know that for every S n the corresponding result holds. So, what does that mean? That means, for every S n the integral of the non-negative function S n x y d mu cross nu x y is equal to the iterated integral. So, let us write, say for example, integral over x, integral over y, S n of x y d nu d mu, and similarly the other iterated integral. Now, what we are going to do is observe the fact that for every S n this result is true, and S n is a non-negative sequence of non-negative simple measurable functions increasing to f. So, by the definition of the integral, this one converges to the integral of f x y d mu cross nu of x y. So, this is by the fact of monotone convergence. This is not really monotone convergence theorem. This is actually the definition of the integral. So, if f is a non-negative measurable function, then its integral is defined as the limit of any sequence of non-negative simple measurable functions increasing to it. So, that is by the definition. On the other hand, we will compute this integral and show it is the corresponding iterated integral of the function f. So, let us look at this integral. So, integral over x, integral over y, S n of x y d nu d mu. So, this we want to show claim that this converges to integral over x, integral over y of f x y d nu d mu. So, this is what we want to show, and once that is shown, so on one hand this converges, right. So, this converges to this iterated integral, on the other hand this converges to this integral of f. So, these two will be equal and we will be through. So, let us try to prove that this iterated integral converges to this iterated integral. So, for that let us observe first that S n. So, note, so here is are the steps for proving this. So, first of all let us try to prove that integral over y with respect to nu converges to corresponding integral. So, for that let us note that S n of x y is increasing to f of x y for every x and y. So, if we fix x, then we get a function y going to S n of x y for every y belonging to y. And because S n itself is increasing, so this sequence of functions we already know these are measurable functions. Okay. these are measurable functions. For every simple function, we had seen that if you fix one of the variables, the other one is a measurable function. Okay. For simple functions, that is true. First of all, this is clear that for fix x, this is an increasing sequence of non-negative functions. Okay. So, this is a sequence of increasing sequence of non-negative functions, and each one of them is a measurable function on y. And second observation is that each one of them, so the function y going to S n of x y is a measurable function. Well, that is in a sense obvious, because to see this we note that, so for this, so observation is, so let us say S n, so let S n be equal to something. So, sigma, say let us say it is a I n, indicator function of E I n for some I equal to 1 to some indexing set 1 to m n. Okay. Then for every fixed x, so for x fixed, y going to the indicator function of E I n x y is measurable. So, that we have already observed. Okay. That is a measurable function. While computing the product measure, we saw that this is. So, each one of them is measurable with respect to the product sigma algebra, because it is the indicator function of a set, and for every fixed x, this will be a measurable function on y. So, there will be the sections. Okay. So, that will be the measurable. Scalar multiple of a measurable function is measurable, and the sum of measurable functions is measurable. So, this is an obvious fact that for a simple measurable function S n, if we fix one of the variables, in the other variable it becomes a measurable function. So, this is a measurable function. Okay. So, that means for x fixed, so what we have gotten is for x fixed, the sequence S n x y over n is a sequence of non-negative b measurable functions on y, and also it is increasing. In fact, it increases to, so what does it function? It increases because S n increases to f. So, when we fix one of the variables x, this is going to increase to the function f of x y, x fixed as a function of y. So, increases to the function y going to f of x y. So, it is a perfect setting for application of monotone convergence theorem. So, by monotone convergence theorem, we get the following. So, by monotone convergence theorem, we get, so to this applied monotone convergence theorem. So, by monotone convergence theorem, the integrals S n x y d nu y over y, limit of that must be equal to integral of f x y with respect to d nu y. So, this is what we get. Of course, for every x fixed. So, for every x fixed, we get that this limit must be equal to this, right. So, that means what? That means this function. So, this is a function of x. So, that implies that if I look at x going to y, f of x y d nu y, if we treat this as a function of x, then it is a limit of these functions, okay. Limit of non-negative simple integrals of non-negative simple functions. So, that means that this function is measurable. So, that implies okay. So, this implies that this function is non-negative measurable. It is a non-negative measurable function. Okay. And this is a non-negative measurable function, and it is a limit of this sequence of non-negative measurable functions. So, by star I can apply again another application of monotone convergence theorem. So, this limit of this on the left hand side, the limit of integrals of Sn's with respect to nu, that also is a limit of measurable function. So, this itself is a measurable function with respect to x. Okay. And because Sn's are increasing, these integrals are also increasing. Okay. So, this is so if we call okay. So, this limit is equal to this. So, now what we are saying is another application of monotone convergence theorem to the fact that if you look at the sequence okay, of measurable functions, this is a measurable function. Okay. So, integral of that. So, let us write. So, the function x going to this is a non-negative measurable function. So, what is left to be proved? We want to integrate this with respect to mu. Now, so that is what we are saying, that to this we apply monotone convergence theorem. So, we will get that limit of these functions is this function. So, integral limit of the integrals. So, this says limit n going to infinity integrals of this function. So, integral over x of these functions are S n x y d nu y d mu x. So, this limit of this must be equal to integral of this with respect to x, again by monotone convergence theorem. So, let us write that. So, this is equal to integral over x integral over y of S n x y d nu y d mu x. So, this limit is equal to this. Okay. But on the other hand, we had seen that this iterated integral for S n's okay, that is equal to the double integral. So, this is one thing of one observation. Okay. Also, so let us look at the other fact. So, what is the other fact? So, also we have that integral over x integral over y S n x y d nu y d mu x. For simple non-negative simple measurable functions, the claim holds. That means, this is equal to the double integral the integral over x cross y of S n x y with respect to the product measure mu cross nu. Okay. So, this is because we have already proved in step 2 that the result holds for non-negative simple measurable functions. Okay. And now, if I look at so this result is equal to this. So, limit of this must be equal to limit of that. Okay. So, implies the limit n going to infinity of this left hand side must be equal to limit n going to infinity of the right hand side. So, this one, and that is coming here. But limit of the left hand side okay, we have already seen is equal to the limit of the left hand side, we have already seen it is equal to this. And what is the limit of the right hand side? S n is a sequence. So, we have already seen that S n is a sequence of non-negative simple functions increasing to f. So, this must be equal to integral x cross y of f x y d mu cross nu. So, that proves that this must be equal to this. So, that proves that the step 3 proves that the integral of f x y with respect to integral of Okay, let us just see have we proved that. So, what we have shown is this limit must be equal to this, and what was that limit of that quantity. So, what we have shown is that integral of d mu cross nu, okay, is equal to over x cross y is equal to limit n going to infinity of integral over x integral over y of S n x y d nu y d mu x. So, this is what we have proved just now, that this okay, this limit on one hand side was this, other hand side was this. So, limit of these two quantities must be equal. So, this is what we have proved, but this quantity, let us see what is this. So, note that see S n for every y fix was increasing. So, just this look at the sequence for every x fix, that is an increasing sequence of non-negative measurable functions increasing to the function f of x y. So, monotone convergence theorem says this inner integral, okay, converges to integral of y f of x y d nu y, right. That is what we had already observed. And then again this is a sequence of non-negative simple non-negative measurable functions. The application of monotone convergence theorem gives us that integral of this limit of that must be equal to d mu of x. So, that says that the double integral of the non-negative simple function is equal to the iterated integral of the non-negative measurable function iterated first with respect to nu and then with respect to mu. And we can interchange x and y. So, same arguments you will imply. So, that let us say that this is also equal to integral over y integral over x of f of x y d nu y d mu x. So, basically, so let us just go through the ideas in the proof, that basically this proof is an application of the fact that integral for a non-negative simple function is built from the limits of integrals of non-negative simple measurable functions. So, and that fact is used very effectively, because we know that the corresponding result is true for indicator functions and integration is linear. So, that allows us to say that from the indicator functions you can go to non-negative simple measurable functions by just taking scalar multiplications and additions of characteristic functions. So, that will give us that the result is true for non-negative simple measurable functions, and then just an application, some suitable applications of monotone convergence theorem will give us that the integral of a non-negative measurable function on the product space can be computed via the iterated integrals.